Welcome back. In this video, we're going to continue looking at the properties of liquids by evaluating what we call a phase diagram. The phase diagram is a way to depict the various phases that a substance can be in as a function of both pressure and temperature. Then we're also going to compare how phase diagrams and heating curves are related to each other. So a phase diagram looks at the pressure of a substance versus the temperature and shows the boundaries between various phases. So for a phase diagram, you can use this to predict the actual state of matter as a function of temperature and pressure. You need to be familiar with and be able to identify the three different phases of matter on a phase diagram: the triple point, the critical point, the coexistence curves, and the normal, melting, and boiling points. Now let's talk about why the phase diagram is organized the way that it is, why this makes sense. If you were to take a substance, and let's say that we take let's say we take a gas at atmospheric pressure. That's what we are referring to in terms of the normal boiling point. If you take that gas and you decrease its temperature, what's going to happen? Well, it will first condense into a liquid, and then it will freeze into a solid. So when we look at a phase diagram, what we can see is that we have gas on the right and solid on the left with liquid in the middle. If you were to take a substance and you increase the pressure of a gas, let's say right here. When you increase the pressure, that compresses the volume which it occupies. That's going to increase the strength and number of intermolecular forces. And eventually, you can obtain a phase change. Because at that point, the strength of the intermolecular forces is larger than the kinetic energy. The triple point is the point at which all three phases of matter coexist and can convert between each other. So you can have solid melting to liquid, liquid vaporizing to gas, gas doing deposition down to solid, solid subliming up to gas, all of that occurring at that specific temperature and pressure. Past the critical point, we have what we call plasma. Plasma is a state of matter that shares properties of both liquid and gas. You don't need to know much about it other than that's what occurs past the critical point. And once you've turned it into plasma, you're not able to reconvert it back into liquid or gas. It retains its plasma-like qualities. And you have to obtain very, very high temperatures and pressures in order to make that occur. The different colored lines that you see here, these are what we refer to as the coexistence curves. And they're called that because the substance can coexist between the two phases on that line. So what we see is that there are a variety of temperatures and pressures at which a solid can melt and become a liquid, or which a liquid can vaporize and turn into a gas, or solid into gas or gas into solid. You also need to be familiar with the changes that are occurring. So being able to label using a phase diagram, whether it's melting, whether it's freezing, if it's vaporizing, if it's condensing, if you're doing sublimation or deposition. There is a relationship between the phase diagram for a substance and its heating curve. If we were to look at a substance's identity and what's happening in terms of the temperature, what we can see is that if we were to take a substance and increase its temperature by increasing the heat, that initially, if we're starting the solid region, we can then convert and melt here at the coexistence curve. We then increase its temperature. We then vaporize the substance, and we increase its temperature again. So we see that we can relate a phase diagram and a heating curve. Something for you to think about is, what if we had a phase transition occurring at a different location? What would the heating curve look like at that point? Well, for this green arrow, we see what we're doing is sublimation. So we're converting from solid to a gas, but we don't do the melting process, and we don't have it in a liquid phase. So those portions of the heating curve would be gone. If we had a heating curve made out of this blue line, it would be similar to our red heating curve, but the lengths corresponding to the temperature changes would be different. Now, what if we performed this change? What we see here is that we're increasing the temperature, but then we're decreasing the pressure. So that wouldn't be as easy to depict using a heating curve, because heating curves only look at temperature as a function of heat. So what we would see would be happening is that would be increasing the temperature of our liquid, and then suddenly it converts to a gas with no change in temperature, only a pressure change. Let's do a practice problem here. What happens to the melting points of water and carbon dioxide as pressure increases? Look over these phase diagrams and see if you can figure that out. Pause the video and try it on your own. Welcome back. So the easiest way to think about this is to draw a vertical line somewhere along the melting point. So when we're talking about melting points, it doesn't specify here if we're talking about the normal melting point or some other place. Notice that for carbon dioxide, we don't have a normal melting point. It always is occurring at very high pressures. But if we increase the pressure, what happens to the temperature at which it melts? What we see is that the melting point for water is decreasing. Notice that our line is slanted backwards, such that the temperature at which it's melting is going down. Whereas for carbon dioxide, the temperature at which it melts is going up. Water is very unique in this sense, and it's actually related to how water forms its hydrogen bonds. We're not going to go into great detail about that, but you should be able to interpret phase diagrams like this for any substance if you're given them. That's it for this video. Thanks for watching. Have a great day.